All right, we're back. We're on page 308. We're on the first page of notes 22, which is the last set of notes for math analysis. Huge accomplishment. So let's power through these and finish strong. We're just going to talk about things we can do with derivatives. There's all this information that we've got: limit definition, multiple versions of the limit definition. We know that there's a power rule, product rule, quotient rule, sum and difference rule, constant multiple rule, a lot of rules for derivatives. We've talked kind of casually about how we can use the derivative to see where a function is increasing and decreasing and all of that. What we're going to do is try to formalize some of that, do some examples, and just kind of go from there. So still a lot of learning to do, but there's kind of like a light at the end of this tunnel. What that light is it's the giant blaring spotlight of calculus, which is what you'll probably be doing next, but we're on our way. So let's get this going. So we're going to talk about extreme values of a function. So first, there's like a little bit of terminology. So let me just kind of highlight a few things for you here. So the maximums and minimums are the extreme values, right? So the most extreme thing you can think of is like the peak of whatever. So extreme values are often called extrema, which is singular. No, it isn't. That's plural. Extrema is plural. Singular is extremum, and you will never see that. Like, no one uses that word anymore. So what does it mean for something to be an extreme value? All right, so there's two concepts we need to distinguish. There's an absolute maximum or minimum, and then there's a relative maximum or minimum. And if you think about it, like one of them, so like the absolute maximum is being the absolute best of all time, or like in the league or whatever. Relative maximums that's about being the best at a particular time rather than of all time, or the best on your particular team rather than the best in the league, right? So one of them is like global, the other one is kind of like a local type of thing. So extreme values on an interval. Not super in love with this notation, but let f of x be a function on an interval I. Okay, so I, these are x values. So it's kind of like the domain. So it's like a function on a particular domain. And let a be an element of I. So a is just an x value. So then we're going to say that f of a, which is a y value, right? So this is a y value. So that's actually a big deal to think about, is a y value. So f of a is the absolute minimum of f of x, of the function, on the interval, on its domain, on this particular domain. Now this is a little weird, right? You got to really think about this. If f of a is less than or equal to f of x for all x on the interval. So what does that mean? That means that you can get the same y value multiple times. It's just talking about the y value. So like maybe you have a function that does something like this, right? So this, let me zoom in here. Okay, so here, if these points are on the same horizontal, where even is my phone? Sorry, I got a text message, really loud. It's like on it's on a relatively empty cabinet, and so it just amplifies the vibrations there. So this y value is the smallest y value. It just happens to happen more than once. So that can happen. The same can be true for an absolute maximum. So for an absolute maximum, it can occur more than once. So it's the same idea. I'll highlight in a different color, because you gotta vary it up. But it can happen more than once, because all we're talking about is the y value. Like the best score that you ever got on something was a 98, and you did it like 5 times. So 98 is the absolute max score you ever got. You just keep getting it over and over again. So it can happen more than once. So there are two things that can really, really mess up whether or not you're going to have an absolute maximum or an absolute minimum. And those two things are as follows: discontinuities. So a discontinuity could prevent, it doesn't need to, but it could prevent you from having an absolute max or an absolute min. So the example here that I've given is tangent, right? So think about the graph of tangent. So I'm going to put in some tangent lines here. Not tangent lines, some asymptotes. And then let's sketch in. So there's tangent. Tangent does not have an absolute max or an absolute min on its domain. We could restrict it, but there just isn't one, right? Because you go up to infinity, you go down to negative infinity, there's no absolute max or min. So if you have discontinuities, it is possible that you will have no absolute max or min. You could also have an open interval. So if you just graph x cubed, which I'm going to do really tiny over here. So x cubed doesn't have a max or a min because as x approaches infinity, x cubed approaches infinity. As x approaches negative infinity, x cubed approaches negative infinity. So that's just not going to happen for you. So discontinuities in open intervals, they're a problem. Let's see if we can think about this. So find any absolute extrema, so absolute max, absolute min, of f of x equals x squared minus 9 on the given intervals. All right, so I'm going to do this basically by graphing. So I start with this. And then I'm going to put this at -9. So I guess this is 3 and -3. Not really worried about those because they don't really convey the information that we're looking for. And then drawing quadratics is like way harder. I say it all the time. Maybe I just have a problem with it, but I think it's way harder than people give it credit for. Okay, so you can look at this and you can say like, there's definitely no absolute maximum because it's just going to keep going up forever. But right here, whoa, where are you going? Okay, right here, we can definitely say the absolute minimum is -9, and it occurs at x equals 0. So the minimum is the y value. Where it occurs is almost usually inconsequential. Like you usually don't really care about that. So this has an absolute, it's an open interval, and we do have an absolute minimum. We don't have an absolute max. You didn't have to because of the open interval thing. How about this? So this is a weird one. So it's the same function, but now it's only from 0, not inclusive, to 4, inclusive. So let's sketch that. Okay, so at 3, I'll have a 0. At 4, 16 minus 9, so it'll be at 7. This is going to be terrible. And then not to scale, right? Because I'm about to put -9. We can't get to 0, but if we did, we would get -9, so open circle. Oh, yeah, that's definitely not exactly right. Okay, but what's happening? Okay, so you kind of want -9 to be the minimum, but it's not. The limit as x approaches 0 from the right is -9, but you can never get there. So if somebody says like the minimum is -9, you're like, no, you can't get there. You can get to -8.999 or -8.9999, or just keep adding a 9 at the end, but you can never get there. So because this is open, so open circle, therefore no absolute minimum, which a lot of people hate, which is totally okay, but you can't get there. On the other hand, up here, this is the absolute max because that y value is greater than or equal to, but actually just greater than, all other y values on this interval, on the domain that we're talking about. So that's the actual absolute max. So the absolute max is 7, and it happens at x equals 4. So that is an example where it's like a semi-open interval, semi-closed, half open, half closed. I don't really know what the correct terminology would be on that. We had an absolute max. We did not have an absolute min. All right, let's try this one. So -4 to 1. So if I plug in -4, I think I get 7 again. Ooh, I got a keyboard up here. Stop. Okay. Something that I'm doing is making a keyboard pop up over and over. Here we go. All right, so at -4, I'm going to be at 7. So 7, let's go -4, -3. I know that at 0, I'm going to be down at -9. Just try to draw this a little more to scale. And then at 1, I can't get to 1, but if I could get to 1, I'd be at -8, I think. Let me just check. Yes. Okay, so we're going to go, whew, this isn't going to look great. Open circle, there, there, and then there, I guess. That's not terrible. That's not as bad as it should be. All right, so what's happening? Well, -9 is the smallest y value. It happens only once. There's no y value less than that. So right here, we have an absolute min of -9, and it's at x equals 0. Okay, that's good. If you look, we also have an absolute max. So here, there is no y value that will ever be bigger than 7, but you get to 7. So here, this is an absolute max is 7, and it occurs at x equals -4. So it's like we're answering two questions. We're answering, what is the absolute maximum? It's 7. Where does it happen? It happens at -4. More often than not, you actually only care about like what the value is, but I usually answer both questions at the same time because I don't want to risk like not answering one of them when I should have. All right, so what I'm going to do is cut this video here. We talked about extreme values, which are just like, they make sense, right? It's the absolute biggest value, the absolute smallest value. If you have a discontinuity or an open interval, like who knows? But in the next video, we're going to talk about when you definitely will get these things. So I will see you in the next video, and we're going to keep going.